Hello everyone, I am Monika Bhushan and today we are starting partial differential equation lecture number 10. So in today's class we are going to see the solution of Lagrange's partial differential equation of order 1. Okay, so by now we are 100% sure that which type of equation is called as partial differential equation, correct? We know that what is order 1 partial differential equation. In today's class, we are going to learn that which partial differential equation is called as Lagrange's partial differential equation and how to find the solution of it. Okay, so if I will write down the equation in this form, this is P x comma y comma z del by del x of z plus q x comma y comma z del by del y of z equals r x comma y comma z. So first thing is what these all things are there right now. So this we know, right? Del by del x of z is nothing but partial differentiation with respect to x of z, and this only we write as p. Fine. Now we know that del by del y of z is nothing but q. Fine. So this same equation we can write in simplified form as p, and then small p is my del by del x of z plus q, and this is my q, small q, equals r. And what does it mean? Why I am writing down x comma y comma z? Because p, q and r are the functions with respect to x, y and z. Okay, so that means if I will talk about this first term says that this is my del by del x of z, this is small p. The coefficient of p is capital P. And what is this capital P? Capital P is any function with respect to x, y, z. Similarly, if I will talk about the second term is nothing but this is my small q, and then small q has the coefficient which is a function with respect to x, y and z. Okay, similarly this is the right hand side will not have any partial derivative. This will be having any function with respect to x, y, z. Okay, so this equation or this form of partial differential equation is only called as Lagrange's partial differential equation. Okay, so this is my Lagrange's partial differential equation, and if we will little bit elaborate more on this equation, so for sure this equation is of order 1. Right now, why this is of order 1? Because here I am seeing that first order derivative, that is p and q. Here we won't be dealing with RST. What are RST? We have seen those things right now. Del 2z by del x square, or del 2z by del y square, or del 2z by del x del y. So these things will not be seen in your equation. Fine. So that means here we will be having p and q, and these things will be in my left hand side. Right hand side will not have any partial derivative. Okay, the second thing is this equation is called as quasi-linear partial differential equation. So why we call it quasi-linear partial differential equation? Because here the degree of p and the degree of q are 1. Okay, and the other thing is the coefficients of p and q, that is this capital P, capital Q, so they are actually functions of x, y and z all, right? And the right hand side also contains x, y, z. So what is the difference between linear partial differential equation and my quasi-linear partial differential equation? So if I will write down the general form of linear partial differential equation, that means, so this is the linear partial differential equation general form. So the difference, if you will see from this form and this form, is here the coefficients of p and q are actually the functions of x and y only. Here you won't find z term. Okay, and even in the right hand side, this is the function with respect to x, y, and which is multiplied with z. Okay, and this is another term is x comma y. So the main difference here you will find out that in right hand side this is the function with respect to x and y, and it is multiplying with only z. That means the power of z will always be 1 in your linear partial differential equation. And in your quasi-linear partial differential equation, right hand side will contain function with respect to x, y, z all. Okay, that means the power of z here, not necessarily the power of z should be 1 only. Here it will be 2, 3, 4, anything will go. There is no problem in that. So one example if I will give you for linear partial differential equation. So this is the example of linear partial differential equation. So the difference, if we will focus between linear partial differential equation and quasi-linear partial differential equation, will be with respect to this z. Okay, because here also you will find that the power of p is 1, power of q is 1. That is okay. The same thing will be there in my quasi-linear PDE also. But here your coefficient of small p and coefficient of small q are not containing z term. In my quasi-linear partial differential equation, we are allowed to write z also. Okay. So, and one thing is there that not necessarily all terms, okay, not necessarily, I mean, all coefficients will always be containing x, y, z. We have the option given that x, y, z all are allowed in quasi-linear partial differential equation. This says that the coefficient of p will be containing x also, y also, z also, but not necessarily always it will be containing x, y, z. But in my linear partial differential equation, we will never be having z as the coefficient of p. Okay, I mean no any function will contain z as the coefficient of small p or coefficient of small q. Okay, one thing. And the second thing is here we have x, y, z only, that is valid in my linear partial differential equation. But in my quasi-linear partial differential equation, I can write here z square also, or maybe z cube also, because this will be the function of x, y, z. So we can say that this is the example of quasi-linear partial differential equation. If I will relate this equation with Lagrange's partial differential equation form, so we can say that my capital P in this equation is what? Zx square. My capital Q in this equation is xy, okay, and my capital R in this equation is what? This will be my xyz square plus xy. Okay, so this is again in the form of capital P small p plus capital Q small q equals R. That means this form of equation is eligible to solve using Lagrange's partial differential equation solution method. Okay, so first thing we should be knowing that how to understand that, suppose in any question has come in your paper, whether I should use this Lagrange's form of partial differential equation method. So first thing is we need to understand thoroughly that which form is my Lagrange's partial differential equation. So if I'll give you one example of non-linear partial differential equation, though this can be your x square p square, okay, plus y q equals something equals z. So since the power of p you can see more than 1, so this type of equation you cannot solve using Lagrange's partial differential equation method, because this is your non-linear equation. Since we understood that Lagrange's form of partial differential equation is capital P plus capital Q equals R, then now we have to understand how to find the solution of this type of equation. Okay, so the solution of Lagrange's form of partial differential equation is actually phi u comma v equals 0. Okay, so what does it mean? Why we are writing down phi u v and what are all these things? So phi is the arbitrary function, okay? So phi is any arbitrary function and u is nothing but some relation of x, y, z. V is again some relation of x, y, z, and they are nothing but some arbitrary constants, okay? So I'm just writing down u, which is the relation between x, y, z, is nothing but some arbitrary constant c1, and v xyz is nothing but arbitrary constant c2. Okay, But from where we have got this u and v, first thing, and second thing is why we are equating them with some constant c1 c2. Okay, so this u and v actually we are getting from Lagrange's auxiliary equation or Lagrange's subsidiary equation. Fine. So same way like how we understood that the some specific form is called Lagrange's form of partial differential equation. Similarly, we have some specific system of auxiliary equations given by Lagrange. So that is nothing but dx by capital P equals dy by capital Q equals dz by capital Z. Okay, so this auxiliary equation is going to be very helpful to find the solution of Lagrange's partial differential equation. Okay, so as we said that this phi is arbitrary function, u and v are solutions of this Lagrange's auxiliary equation. Okay, and this c1 and c2 which we are relating them with as constant, this C1 and C2 are actually characteristic curves of Lagrange's auxiliary equation. Okay, so we relate them as arbitrary constant. So the concept is x and y are two independent variables and the solution of this Lagrange's auxiliary equation is integral surface. So because of that only we have got some arbitrary constants also. So this integral surface actually gives us some idea that we have to perform some integration also in the method of solving of this partial differential equation. Fine. So to get this u and v, two solutions for Lagrange's partial differential equation, we will be dealing with two methods. First method is called as grouping method. Second method is called as method of multiplier. And the third method will be combination of grouping and method of multipliers. And we will be having one more lecture on some specific type of questions where grouping and method of multipliers both also, if we will be applying, it won't be that easy to solve. So that will be some special form of questions. Okay, so those special questions we will be seeing. So these things will be actually covered in four classes. So in today's class we are going to see method of grouping. So what is this method of grouping or method of multiplier or combination and all? They are to find the solution of Lagrange's PDE. And the solution will be what? This is your u and v. That means your answer will always be containing phi u comma v equals 0. This form we will be writing down. So this phi will be your arbitrary function. This u and v, two independent solutions we need to write down, and that solution will be in the form of xyz. Fine, and those things will be nothing but the constants c1 and c2. Okay, so here is the question. So we will be solving these two questions, and today's class we are going to actually follow the method of grouping. Fine. So very first thing is, suppose this question has come in your exam, how you will understand that you have to use method of grouping or whether this is my Lagrange's partial differential equation, how I'm going to solve. So very first thing is you just make sure that this is in the form of Pp plus Qq equals R. And how this is in this form? So here you will say that this is your del by del x of z, this is my small p, this is your del by del y of z, this is your small q. So whatever is the coefficient of p, so this is your capital P, y square is your capital P, and your q, capital Q is your minus xy, correct? No, because this plus is there. So you got to know that, okay, left hand side is actually coming in the form of pp plus qq, and the right hand side is not having any term which is pq. So that means this is your some relation, some function with respect to xyz. That is okay. So this is my Lagrange's form of partial differential equation. So we can move on solving by method of grouping first. Okay. Fine. So here is the question. So what we have to start with, we are going to check that, okay, this is in the form of Pp plus Qq equals R, and we notice down that what are these three things. Okay. So the very first step we are done with. What is my second step? So this was your step number 1. What is my step number 2? So like how we came to know that this form is called as Lagrange's form of PDE. Similarly, we have Lagrange's form of auxiliary equation right now. So the auxiliary equation we will be first writing down, and that is called as Lagrange's subsidiary equation also. And what is Lagrange's auxiliary equation? So this is your dx by p equals dy by q equals dz by r. Okay, so this is nothing but the system of equations, and through this system of equations we are going to find what are two independent solutions. Those two independent solutions will be written as uv, and my final answer will be phi u comma v equals 0. So this is the method which we have to follow. So to get these two solutions UV, we are in this class going to start with the method of grouping. So what is method of grouping? So you can see that three fractions are given here right now. We have written down P, Q, R also. So till here, I think we don't have any doubt. So we can see that three fractions are there. Okay, so method of grouping says that just try to solve using two fractions, either fraction number 1, 2 or 2, 3 or 1, 3, or so that the final fraction what you are going to get will be easier to integrate. Okay, that means suppose I am just talking about fraction number 1 and fraction number 2. That means dx by y square equals dy by minus xy. So what I can say here? I can say that the denominator is having y square and minus xy. So I can cancel one y from here and one y from here. That means I can write down this is nothing but dx by y equals dy by minus x. Okay, and why I'm taking these two fractions? Because you always try to group these two fractions where you will be having, suppose here you have dx and dy, that means z term is not present, or if z term is present, suppose z was there, so you can easily cancel out that z. The reason, because if z will be present, then you won't be able to integrate that, right? Because you have to integrate with respect to x and with respect to y in this fraction. So better to choose in such a way that if x and y are present, so the denominator also contains x and y, and similarly if x and z are present, so that your denominator will be free of y and so on. Okay, so this form is okay, because I can write down here minus x dx equals y dy. Fine. And why I'm doing in this fashion? Because what we say that I am actually focusing on to find u and v, and u and v are nothing but, finally it will be nothing but my arbitrary constants c1 and c2. Okay, and to get arbitrary constant c1 and c2, we have to actually find out the integration at some particular step. So here if I'll find out the integration of these left hand side and right hand side, so I will get some integral surface, because we know that u and v are nothing but the solution of integral surface. So I can mark it as step number 3. Okay, because step number 1 was to check what is my capital P, capital Q. So step number 2 is try to make some kind of grouping so that it will be easier to integrate. And step number 3 is find out the integration. Okay, so here if I write down the integration, it is nothing but minus x square by 2. Okay, and then right hand side is your y square by 2, and then plus I'm writing down some arbitrary constant. Okay, so here also actually it will be some arbitrary constant, and here also some arbitrary constant, left hand side, right hand side, but I'm writing down only in my right hand side. Okay, so this is your some constant name if I'm giving as c1. Okay, so this is the integration part. Fine. Here here something we need to actually understand, that if I'm writing down c1, what is this c1? C1, I don't know what is C1. C1 is some arbitrary constant. Okay, for sure that this is some constant. Okay, so what I am writing down here, if I will make as C1, instead of C1, if I am writing down C1 by 2, that also will not make any much difference, because even C1, what actual value of C1 is there, that I don't know, right? One thing I'm sure that this is some arbitrary constant. So instead of C1, I can write down C1 by 2. Okay. The reason of writing C1 by 2, not C1 by 3 or C1 into 2, because I want to make this equation simplified form. Because I can see that here also left hand side also has denominator 2, right hand side also has denominator 2. So if I make here also of C1 the denominator 2, then I can cancel out these denominator which are 2, right? That means I can write down minus x square equals y square plus C1, or you can give some other name, C1 dash or C2 or C3 C4. That is, I mean, the main focus is I want to know that what is the relation between x and y. Okay, so here C1 is nothing but minus, I will write down x square minus, I'm taking common, so x square plus y square. So I can say that C1 is minus x square plus y square. Even there is no problem if I will write down further C1 equals x square plus y square. That means I am just neglecting this minus also. And what is the reason? Because again I am not interested in what is actually C1 value or something. I am just saying that I am interested in the relation between x and y, and C1 now also I don't know what is that actual value of C1, that is some arbitrary constant. So the constant can be multiplied or divided or added or subtracted by some constant, and can be actually positive, negative. If I'm making some difference, that also will not have any problem, because C1 I got here as, so C1 I got here as x square plus y square. Fine. So this C1 only I will be replacing it with u. That means one specific solution. That means one solution I have got of this Lagrange's auxiliary equation, that is nothing but x square plus y square. So in the form of like this phi u comma v, u I have got u, instead of u I will be writing down x square plus y square. But I need to know what is this v. Okay, so to get this v, again I am going to follow the same method. What is that method? I am again going to just check my step number 2. That means I am going to apply method of grouping. Method of grouping is the easiest method to get the solution of your Lagrange's partial differential equation. In the next class, we will be seeing method of multiplier. When we need to find method of multiplier, those all things we will be seeing. But in today's class, we are just focusing on the method of grouping only. So in this method of grouping, what I can further think of, I just have to think of these three. Suppose these three fractions are given, which two fractions I will take so that it will be easier in my step number 3. That means it will be easier to integrate. And how two fractions will be easier to integrate? If I am using dx dy, that means z will not be present. Otherwise, I won't be able to find the integration. Fine, no? So this is the concept of taking two fractions, considering two fractions as the in my step number 2. So what next I can see? I have equated 1 and 2. Suppose if I'll equate 2 and 3, what will happen in that case? So 2 and 3, that means this is my dy and dz. That means x should not be present. Otherwise, I won't be able to integrate. So I can see that 1x I can cancel easily, so that these two fractions will be only dependent on x, only dependent on y and z. So that also we can take. But can we take 1 and 3? So 1 and 3 we cannot take, because in my 1 and 3 the denominator should not contain y. Okay, no, because this is your dx and dz. So y square and y square I cannot cancel, so I am taking these two equations. Okay, fine. So we will be seeing, yes, we got u. Now we are considering last two fractions. That means I can easily cancel x and x. Now I got minus dy by y equals dz by z minus 2y. So my second step also done. Now I'm going to start my step number 3. That means I'm going to find out the integration. And why we find integration, why my third step is demanding integration? Because we say that u and v are the integral surface. They are the solution of Lagrange's partial differential equation. So to get the answer of that, I need to actually find the integration part, okay? And that integration part will only give me the constant, arbitrary constant c1, c2. Okay, so what I'm writing down here, I'm just taking z minus 2y in my left hand side, and then minus is present, and then dy, and then I'm writing y dz. So I'll simplify it, minus z dy plus 2y dy equals y dz. Okay, what next I can do? So I will be writing down, and I'm taking this minus z dy into the right hand side. It will be my 2y dy equals y dz plus z dy. Okay, what is this y dz plus z dy? We know the formula, right? So left hand side is 2y dy, and right hand side I can write down dyz. Is that okay? Dyz will give you how much? Y dz plus z dy. This is the formula. So I will put the integral sign in both sides because now it is easier to integrate. Okay, so this is your left hand side will give you 2 into y square by 2, and plus c I'm not writing because in one place in the right hand side only I will be writing down, equals integral, and d will be taken off, and this is your yz. Fine. So here we got this is yz, and plus some arbitrary constant c2 I'm writing down. Fine. So this is your y square equals y plus z, y square equals yz plus c2. That means my c2 is y square minus yz, or I can say that c2 is the arbitrary constant which I am replacing with my v. So this is v. V is the solution of my Lagrange's partial differential equation. So v I got nothing but y square minus yz. Okay, so we got here. So finally the solution we have got here. Fine, no, this is your u and this is your v. And u, v are actually your c1 and c2. Fine. So now we will be seeing the second question. So this second question, suppose this has come in your paper. So again, whether you have to start with grouping method or what, before that you need to be thoroughly understood that whether this equation is in Lagrange's PDE. So P you can see, Q you can see. That means you can check the capital P and capital Q also, because here you are not seeing any RST, even you are not seeing P square or Q cube. That means they are in linear form only. So you can start thinking of whether this is my Lagrange's PDE form. So yes, this is my Lagrange's partial differential equation. So before that we can see that the first term actually contains z in my denominator. So I'm just simplifying it. Okay, that means what I'm writing down here, I'm multiplying each and every term with x. Fine, no, if I'm multiplying each and every term with x, so the denominator of first term will go. So that means my first term will become y square z p, second term will become x square z q, third term will become x y square. Fine. Now I can write down what is my capital P. So capital P you can see here, capital P is y square z, capital Q is your x square z, and capital R is your y square z, is your y square x. Fine. Now my first step is done. My first step was just to make out my PQR. So I understood that what is my PQR. Now I'm going to write down my step number 2. Step number 2 is what? Write down Lagrange's auxiliary equation. That means the solution will be actually u and v that I'm going to get by solving this Lagrange's auxiliary equation. And Lagrange's auxiliary equation is what? Dx by p equals dy by q equals dz by r. Right now, first step was to understand PQR, what are my PQR. Second step is to solve Lagrange's PDE. What is the solution? That is your phi u comma v equals 0. You have to work on uv, right? But from where you will get uv? To get uv, you have to actually find the solution of Lagrange's this subsidiary equation. Fine, no. So I'm writing down here dx by p. So here it is written dx by p is your y square z. equals dy by q. Q is your x square z, and then dz by r, and r is your y square x. So now I'm trying method of grouping. So method of grouping says us that you just group any two fractions, either fraction number 1 and 2, 2 and 3, 3 and 1, or any fractions, so that the step number 3 will be easier. That means integration part will be easier. So if I will take these two fractions, okay, so then z will get cancelled, fine. So this will be your dx by y square and dy by x square. That will be easier to integrate right now. So I'm down dx by y square equals dy by x square. So my step number 3 is what? I have to integrate it. So to integrate, I'm taking x square towards my dx. So it is your x square dx, and this is your y square dy, and finally I am going to integrate. The reason of integrating in my step number 3 is what? I am interested in that arbitrary constant C1. Fine. So that C1 I will be getting after my integration part. So this is your x cube by 3 equals y cube by 3 plus C1. C1 is some arbitrary constant. Again, the same concept I am going to apply, that instead of C1, I can write that instead of C1, I can write C1 by 3 here only, or you can write C1 dash by 3, anything, right? No. So here I am writing down C1 by 3 because C1 is any arbitrary constant, C1 by 3 is also any arbitrary constant. So I am not violating any rule, because just to make the equation simplified, I am writing down C1 by 3. So I can write x cube equals y cube plus C1. Or I can say that my C1 is x cube minus y cube. That is the constant of my integral surface. So that means u is x cube minus y cube. Fine. Now I'm going to find out what is my v. So to find v, again same step I'm going to follow. That means in my step number 2, I'm going to make some other grouping so that the integration part will be easier. So if I take my second and third fraction, so here what should be my goal? My goal is, if it is my dy and dz, so x term should not be present. But here I cannot cancel x. If only one x will get cancelled. So let me try 1 and 3. So if I am making grouping of 1 and 3, so in that case, this is your dx and dz. That means y term should not be present. So here you can see y square you can easily cancel out. So that means it will be your dx by z equals dz by x. Fine. So here we got our u. Now we are talking about the second grouping. So yes, we have written down here. That means what I am writing down here, this will be your x dx equals z dz. Fine. And now you are going to write down x square by 2 equals z square by 2, and then plus c2. Instead of c2, here only I am writing down c2 by 2 to make the equation in the simplified form. So finally I got my C2 is your x square minus z square. Fine. So C2 is only my second solution of Lagrange's PDE. That means V is your x square minus z square. So finally you have written down the solution, which is some arbitrary function phi, and then you have just now got, and then V is x square minus z square equals 0. So this is the method which is called as method of grouping. So in next class, we will be solving Lagrange's PDE only. The goal will be to find this answer only. I mean, the goal will be to find what is u, what is v, but we will be seeing that method of grouping in some questions will not work. So in that case, we will be taking help of multipliers. So that method of multiplier is actually very important in exam point of view. So we will be seeing in next class method of multiplier. So if you find this class useful, please like and subscribe my channel. Thank you.